Alright folks, this is chapter 14 part 2. I screwed up the last video, which is why it's so short, so let's try this again, shall we? Anyway, we just talked about energy efficiency. Now let's talk a little bit about humans and our use of energy historically. So kind of our first, big energy thing was steam power, and originally in the early 1800s, this burned wood, so all your steam-powered turbines, your steam-powered trains, right, these guys were burning wood. Now, that works, but wood isn't necessarily a super, high bang for the buck product, right? In 1859, you can see here, this is, you still go visit it today, the first oil well in the United States in Pennsylvania. In 1875, coal finally replaces wood as the major fuel source for steam power, coal being a much more concentrated form of chemical energy, a lot more bang for your buck than wood. And then in the early 1900s, then, the widespread introduction of the internal combustion engine leads to the rapid rise in the consumption of oil, and that's been the trend we've been on ever since. So let's talk about these different types of fuels here, fossil fuels, and we'll start with coal here. Now, coal, most of the deposits of coal that we harvest are between 2 and 350 million years old. So the idea here, obviously, on our time span, it is non-renewable as far as resources go. It is from the ancient remains of dead plants, mostly, little bit animals, I guess. These are from basically swamp-like conditions, river deltas in, these kind of areas where lots of matter is accumulating. The water is pretty stagnant. It's anoxic, right? No oxygen's getting to this stuff, so it's not being decomposed and broken down. Rather, it's sticking around and accumulating, right? And this happens most often in humid climates, so in tropical type climates, this is occurring, right? In economical deposits, we can harvest ones that are, only 6 inches thick and make that economical, to well over 100 feet thick, depending on the conditions. 6 inches, most of the time not economical, but if there's not a lot of overburden you have to remove, it might be fairly economical to mine. As far as, compaction, why is, there more bang per buck out of coal? Well, it's because it's a very compact form of organic matter. So you take 3 to 10 feet of like peat or compact organic matter. This is only going to give you, say, 1 foot or so of coal. Coal, as it gets buried, right? So it's burial and temperature. That's going to help to increase in the compaction, right, and increase the chemical potency of the stuff. So burial and temperature both help to determine the grade of coal, and you can see kind of the grades of coal here. We start with peat, which is kind of modern and ancient, just not buried or compacted organic matter that's been accumulating. And then you add some heat and some pressure, you start to squish some of the liquid out of it, right? And the first thing we get is this stuff called lignite. Now, this is pretty crappy coal. Yeah, it will burn, but you don't really want to use it. It's full of lots of impurities, all that kind of stuff, right? And as we continue to add more pressure and it gets buried farther down, we get higher and higher grades of coal, subbituminous, and then finally when we get to bituminous and then anthracite, these are the kinds that we're really looking for. These are going to have the most bang per buck, the most concentrated chemical energy. And just here's kind of a look, as what they look like. As you can see here, the lignite's very kind of uncompacted and brittle, right? And then the anthracite is a fairly, compacted, intense form of coal. Beyond anthracite, if you bury it any farther, any deeper, right, when these are carbon-based material here, you're going to force that into graphite, right? Graphite being chemical formula C, right? If you bury that even deeper, what you get is diamond, right? So we go through the coal window, the graphite window, and then the diamond window. There are some pretty bad environmental impacts of using coal. One of the biggest ones is sulfide minerals present in coal. And we talked about this when we talked about mining. Sulfide minerals weather very easily in surface conditions into sulfur, right? Releases sulfur dioxide, which combines with oxygen to make sulfuric acid, drainage, and rain, right? And then the other part of these sulfide minerals is a heavy metal. And when you burn them, you release this heavy metal and you get heavy metal fallout as well. Another, important disadvantage of using coal is it releases tremendous amounts of carbon dioxide. Carbon dioxide, of course, being a very important greenhouse gas to us here. Right? And the thing about, ancient coal, ancient oil, natural gas deposits is this is the Earth's natural way to sequester carbon, right? Take it out of the surface carbon cycle, right? So all of this dead organic material is being sequestered inside the earth. Now what happens when we dig that up, we extract it, and then we use it, is we release that carbon dioxide into the carbon cycle. So it's like digging up all this extra carbon and throwing it into our carbon cycle. So one idea to try to offset this has been, if the Earth naturally sequesters carbon, maybe we can inject it down back into the Earth to sequester it. And this has been done, but to my knowledge, not on any scale large enough to, make a difference globally. Now that was coal. Now let's talk about petroleum. And by petroleum, I mean oil and natural gas, the other two of the fossil fuels. Oil also originates from organic matter, but has a completely different origin story than does coal. Petroleum is also known as hydrocarbons. Hydrocarbon because the molecules are primarily chains of different lengths of hydrogen and carbon. There are considerably more hydrogen atoms even than in coal, so even more so than coal, you get more chemical energy stored, potential chemical energy, more bang per buck out of the oil and the natural gas. Now the natural gas part of petroleum, this is the mixture of the lightest of our hydrocarbon gases, the shortest of these hydrocarbon chains. For example, methane is the lightest of them. It only has one carbon and then 4 hydrogens on it, CH4. The rest of the stuff in a liquid state then is known as crude oil. This is unrefined oil, the stuff that we extract directly from the ground, and then we take it to a petroleum refining plant and turn it into the usable fuels that we have. We'll talk about that towards the end of this chapter. Now, I said petroleum originates and has a different origin story than coal. It is actually a very complex process, and generally in our traditional oil and natural gas extraction, it originates in one area and migrates to a new area, and then we collect it from that new area. It is formed in organic-rich marine shales, so unlike coal, which forms on land in peats and marshes and deltas, this is from deep water, organic-rich marine shales, mainly from single-cell organisms that are living and dying by the trillions, falling to the sea floor and collecting, right? So as they get collected, they get buried. This transforms the mud into a shale, right? As it gets buried, the process of lithification occurs, right? Again, same as coal, we're talking about this matter accumulating in areas with low oxygen. So this organic matter, rather than being decomposed, is preserved. And then burial, heat and pressure then transform this organic matter. It doesn't start off in the shale as oil or natural gas. It starts off as an organic matter known as kerogen, and it takes depth and heat in order to transform that kerogen into either oil or natural gas. And here is the little graph showing you here. Here's the surface of the earth, and then going down deeper and deeper into the earth. We have, again, like we talked with coal, we have different windows. Up here is kind of the kerogen window. This is what we call the immature stuff, right? This is where it hasn't been buried deep enough in order to transform that kerogen into the hydrocarbons that we need. But once you get down to about 7,500 feet, 7,500 feet to about 15,000 feet, this is known as the oil window. This is when you get to a depth that the heat and pressure is enough. It's going to transform these kerogens into those longer hydrocarbon chains. Now you'll get a little bit of natural gas out of here as well, but mostly oil. Below that, from 15,000 feet to 40,000 feet is known as the gas window. Right? This is where we're going to have more intense heat, more intense pressure, and we're going to break down this kerogen into even simpler molecules. Remember, natural gases are the simplest, the shortest, the lightest of those chains. Right? Below the gas window, the graphite window. Below the graphite window, the diamond window. Right? So, again, like I mentioned, petroleum deposits, whether you're talking oil or natural gas, these are from sedimentary environments, shales, right? And historically, we extract the material, the oil and the natural gas, from a reservoir rock or a more permeable rock, not from the actual source rock itself. Now, shale is one of these interesting rocks. It has a lot of porosity, so it's got a lot of holes and void spaces that this oil and natural gas can live in, but it has very, very low permeability, so very little of these holes are interconnected, and it's very hard for this oil and natural gas to migrate out of the shale. It does, and it can, and it will, and the stuff that does will rise buoyantly, right? Because oil and natural gas are light. They're going to rise buoyantly. Eventually, they'll find a more permeable layer of rock, and they can travel in this more permeable layer of rock, like a good aquifer rock. Anything that would make a good, water aquifer also makes a good natural gas or petroleum aquifer. Right? Now, more recently, we've developed a new technique called directional drilling, and this is going to allow extraction from the source rock itself, from the shale itself, from that organic-rich marine shale itself. So looking at kind of our traditional deposits, right, as this organic shale sits down in the oil and gas window, some of that material does get, so that oil and natural gas does escape and it does rise, right, towards the surface. And eventually it will hit one of these nice permeable aquifer rocks, right, and it's going to travel, laterally then within the water, but of course, being lighter than water, it's going to rise to the surface, right? Rises to the top of that aquifer. But it's important to know that considerable amounts of petroleum still remain in the source rock, still remain trapped in that organic-rich marine shale itself, right? Now, a few other important things that we need to have in order to collect this, right? We must first have some sort of, underground structure, some sort of geologic structure that is going to trap this rising oil and natural gas, right? I mean, otherwise it's just going to keep rising to the surface and eventually dissipate, right? So a few terms here. First of all, petroleum trap. This is any of those configurations, those geologic configurations that allows these hydrocarbons to accumulate. Often is what's known as an anticline, which is an upward bend of the rocks, right? Creates kind of a inverted bowl that helps to trap that rising lighter natural gas and oil. But there's also a few other types like salt traps, stratigraphic traps, fault traps, right? But another important thing you need is to have a reservoir rock, right? So you need to have a rock where this oil and natural gas can be stored, a highly permeable, highly porous rock. And this can hold the oil, the natural gas, or both. But then very importantly, on top of that, you also need a cap rock, which is a low permeability rock, like another layer of shale or something, right? And what this is going to do is to trap that in there. So here's our source, or our petroleum reservoir, right? We would call that an aquifer if we were extracting water from it. And then here's our cap rock, right? This would be essentially the aquiclude or aquitard if this was a reservoir for water, right? And this keeps the oil and natural gas from continuing to rise out, and then we can find this petroleum trap, drill a hole down in it, stick our straw down there, and suck out the oil and natural gas. All right. Now, in order to find these different types of geologic petroleum tracks, we need to do some sort of exploration, and the primary kind used is known as seismic exploration. Just like, we talked in earthquake about seismic waves. This uses seismic waves to look at the underground profile. And what you do is you set up these things called geophones, which are receivers all over in a big grid pattern through the land surface there. And then you set off either dynamite charges, or my favorite way is this guy here. It's called a thumper truck. It's got basically a big hammer pad on the bottom. It just goes bam, 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 bam on the ground, and that creates those seismic waves. That bounces differently on different types of layers with different densities and properties, right? And you can get a three-dimensional profile of this underground area and hopefully locate one of these petroleum traps. Now, if you do locate one of these petroleum trap structures, right, you're going to drill what's known as an exploration well. But obviously more than half of these never even pan out because of all the other conditions that need to be met, right? First, you need to have had a source rock that has been down in the oil or natural gas window, right? Then you need to have a reservoir rock. Then you need to have a cap rock, right? So if all of those things are met, maybe you'll get oil there, but most of them do not pan out. However, if they do pan out, then we put down what's known as a production well. And this is, you've seen these all over, right? This is part of a production well system. This is an oil platform, a drilling platform out in the ocean. This does more directional drilling. We'll talk about that in just a couple minutes here. But so once you find an economical deposit, then you have to put in pipelines, you have to put in infrastructure, roadways, electricity, production facilities. Way back in 2007, this cost more than $4 million per production well, so they're going to want to be pretty sure that they have a good source of oil down there. And of course, these offshore platforms are just, ridiculously expensive. But the thing with this is they're doing directional drilling, and with directional drilling, because you can steer the drill bit underground, you can go out and spider out in several different directions. They'll often do like 8 different directions. Directional drilling, again, is where you steer this drill bit through the subsurface. So you drill down to the layer you want to get to, and this is called the kickoff point, and then you start to slowly turn this drill bit underground till it's horizontal, and then you drill out, say, a couple miles in this direction. Now, the advantage of this is you don't just have to do that in one direction. You can do that in up to 8 directions often. So you can come out this way, you can come down and come out this way, out of the, at the page, into the board, this way, that way, all that way, that way. So, and you'll do that for a couple different miles. And this is recently used in these low permeability but high porosity shale deposits that have been down in that oil or natural gas window, but the oil and natural gas remains locked in these shales. So we actually are able to unlock this oil or natural gas through a process known as hydraulic fracturing. And this is where water, chemicals, and importantly fine sands are forced down into shale under high pressure. First they send off little charges to fracture the rock. This high pressure hydraulic fracturing increases these fractures, pushes sand into those cracks, and then when the pressure is removed, the sand stays in the cracks, keeps them open, and allows oil and natural gas to flow through. This is what we call secondary porosity. We create this secondary porosity here. Now, once we get the oil or natural gas out of the ground, we have to refine it. And the refining process is actually really a distillation process. This is because various chains, these different longer lengths of hydrocarbons, have different densities and temperatures at which they condense. So what we do in a petroleum refining process, we heat up the crude oil. Most of those molecules are vaporized into a gas. that rises into a distillation tower, which is then hotter at the bottom and progressively cooler towards the top. And then these various hydrocarbons will separate themselves out essentially by density, with the shortest hydrocarbon chains are petroleum gases, natural gases up at the top, right? Here's where gasoline we use burning our engines, kerosene, jet fuel, heating fuel, oil, right? Here's where we get our lubricating oils, residue, this is asphalt, stuff like that, right? So heavier towards the bottom, lighter towards the top. And then what we have is basically, little extraction points for these various different now gaseous hydrocarbons. We suck them out, cool them back down into a liquid, and now we can use them and sort them out by their use, right? So here are just a couple videos. The third one's not a big deal to watch, but these first two I would really like you to watch, and I will hold you responsible for the info in there. This first one is by the Marathon Oil Company, and it is a very good visual aid and shows you, goes through the process of hydraulic fracturing very well, but then also gives you a very nice, healthy, clean look at fracturing or fracking. This one has a little bit different look. It's called Fracking Hell, and it goes through some of the potential negative effects of fracking. All right, folks, hope you enjoyed this second video, and I hope it works.